Okay, so we are going to review test 2 question by question, and of all the terrible dysfunction COVID causes, this is maybe one of the silver linings. I hope that it works how I am able to put the question up there, and you can see that, and then I can tell you quite a bit about, I'll go over the answer, but I can tell you like what I was thinking, even when I wrote it, why I wrote it, and that would help you just get it in a more fundamental way, in a more subconscious way that will help you answer. We've got another test coming up, not too much quantum on the third test, but the final is going to have a lot of quantum. Now, the second test was somewhat comprehensive with the first test just because a lot of the intellectual ideas overlapped. So when it comes to studying for the final, of course I'm going to have a final review. I'm going to make that ultra long, by the way. That may be like 3 hours or something. So I'm going to go over time, but I think you would prefer that I cover everything that's going to be on the test than not. So watch that, obviously watch that, but I would also suggest watch this one too. Because again, if prioritize that one, make this your second priority, maybe the first test review, then look at the homeworks. And then rewatch individual videos at will. Okay, so let's just go through them. Question 1. Not my best question, okay? This one, now I did allude heavily to this is one of the times, and a lot of you, not that many, I basically gave the answer during the review session. But not too many of you really got it fully. A lot of you were just trying to remember some fine details of that little video I showed where I compared two potentials where one of them was 10 times longer than the other. So, so what happened was a lot of you said, recalling the video, remembered that the transmission from the thinner one wasn't quite as much as from the thicker one, which is counterintuitive, right? It kind of looked like this, and this area was actually about a third bigger than that one. I don't think I drew it quite right. But the longer barrier actually had more transmission than the thinner one in the example I gave, and that was because when the waves impinged upon the barrier, in the longer one, the wave actually got stuck inside of it. It actually formed like a particle in a box state, and it trapped it inside of it, so it slowly leaked out left and right, allowing a little bit more to leak out to the right than in this case, where most of it just bounced right off. Okay. Now, if you wrote something like that, I accepted it, but the real answer was from that graph I showed of percent transmission versus energy over the potential step, which went something like this. So you may recall that, and this of course is 100%. So the answer, by the way, if you look at the cheat sheet, is that it's complicated. That's the real answer. It's complicated. And some of you did get this right, but you just can't know. You can't know what how much is going to come through a barrier because it's just so non-intuitive. It depends on the energy at which you strike the barrier. It does depend on the barrier height and the barrier length in a really fairly complicated way. Look at the handout on the finite barrier. Remember, I have a handout that works all this out with the formula for the percent transmission. It's really complicated. Which was the answer? It's really complicated. Right? It's not a simple function of the length or height or the energy. I mean, it is a function of the length and height of the barrier and the energy of the wave, and it's a very nonlinear equation. So if you ever need to know this, you have to work it out. Okay. So again, I don't consider that my best question. That's the kind of inside information that might be useful to you, and that's why I'm having this. Okay, part B. Now this was quite a question, right? This was as messed up as I could make it. Now again, I do try to do that. I will try to write as many things wrong as I can without getting too silly, although sometimes I get kind of silly. And this was borderline on that. Okay, so some of the things, a lot of you got this one right. So some of the things to note is the amplitude. I know you can see it up there. I have to draw it for my own benefit. All right, for one, and I did count this right. I said I am asked to ask the transmission, and here's my formula for reflection. I actually would count one of you noticed that I did that. I actually said I'm looking for transmission, and here's the reflection. I do that because you guys tend to do that. I'll ask one thing and you answer another. And I don't give you any credit because you answered the wrong question, but it also made it perfect for what's wrong questions. So that was one thing. The other was that I included a wave. I mean, you can see the question up there. I included an A wave, but not a reflected wave, right? An A versus a B. Some of you clued in that, of course, that there's the same is going on in here. There's a C and a D wave, and that this is actually the exiting wave, which we call the E wave. And that the output here would be as wavy, but have less amplitude as what's on the left. So you notice I'm drawing these with about the same wavelength, but I actually would need to draw them, I actually need to draw it with less amplitude, right? So here I'm just drawing the same thing with about the same wavelength, but with greater amplitude. So, and let's see, last bit was, again, I gave a formula for reflection, and of course I should have been asking for transmission, which would have been the amplitude of let's say, yeah, I would have counted B if you put B, but it really would be, you know, there's 2 waves here, 2 waves here, so that's the 5th wave or the E wave. It would really look something like this. So some of you mentioned that there would actually be 5 different waves here, and that would be the 5th one over the 1st one. Some of you put B squared over A squared. I would have counted that as well. And also the formula is also wrong, so I think there's like 5 things wrong with that one. Okay, part C. Stupid easy. Kind of a stupid question. Again, I'm just trying to come up with something. Okay, so the answer to this question, of course, is to use the log barrier, equate the log derivative on one side to the other. And so there's a couple things wrong here. So again, this is the one with many potential answers, and again, you only need to put one. Now, first is, notice that I have an infinite barrier at 0, but I say that the wave function is cosine. Okay, only one of you clued in that that can't be true. It has to be a sine function, right? Because the wave function would have to be 0 at x equals 0, and cosine is 1 at x equals 0. So that was one of the things wrong. So again, an example of me building several things into the problem that cannot be correct. Okay, I'm not so sure about whether region 2 is correct or not, but you know, here's the thing. Here's another thing that was subtly built into the problem. I said, I was asked, you can see the question, I was asked to write the boundary conditions as a function of psi 1 and psi 2. I never said what psi 1 and psi 2 are. So when I start writing down what I think they are, I'm doing it wrong. And I do that because sometimes you folks do that. So not correct. Okay, then the answer, as you can see right there, is I simply wrote the boundary conditions. I simply wrote the boundary conditions incorrectly. So obviously you have the derivative at a boundary equal to the derivative of the other side at the boundary divided by the wave function itself. And one reason I thought that this, I think this was something that most people did well with, is because of course I had this formula on the cheat sheet. So all you had to do was look it up there. Okay, so that was 1C. 1D is, do you remember? You know, I told you that I try not to ask too many questions of a do you remember the time in class? Do you remember details? I try not to ask questions like this one, but I can't entirely escape it either. So the answer here was, the average wave function is 0. You know, this is 0. And remember, that's true of every different state. So how can the bond length be 0? And the answer is that x represents the displacement from equilibrium, not the bond distance. It's the displacement from the bond distance, not the bond distance. So that's an example of, are you paying attention to these lectures? And I'd say a little over 50% of you got this one right. Now, some of you harped in on, let me give you an example of where some of you, not terribly many of you, got fixated on something that was strange. So I recycled this particular graph over and over again because why wouldn't I? It's just a standard little graph, right? And some of you got fixated on the quantum number. Oh, the quantum numbers, this and that. Why? There's nothing wrong with them, right? So the inside advice here, the cheat code, the hint I can give you, is that those are, these are really small details. I don't try to hide these in graphs with what really is kind of a detail. I don't do that. I make this up front. You should be figuring that out by now. Notice that I don't say anything about the way the quantum numbers in the question itself. I talk about the position. I'm talking about the position, the average position being 0. If you don't address that, you address something else you see in the graph, you're likely getting it wrong. Now, of course, I do hide multiple things wrong in these things, but that's a bridge too far, and it also wasn't the right answer. Okay, now part E, you can see up there. There's not much to this one. It's not really a very well-worded question, but it was another example. What's good about this one, it's another example of where looking at the cheat sheet can give you an answer even when you don't think you need to look at the cheat sheet. Now, most of you got it right. I was very liberal with what I accepted. But a lot of you, if you nailed it, you said, oh, on the cheat sheet, there's this equation. There's this equation. And theta and phi as well. You have to do something like this. Okay, full credit, right? So had you been looking at the cheat sheet, you would have seen the little transformation from Cartesian to spherical that's on the cheat sheet. And you hopefully would have realized that's the answer to this question. Just at least one of the terms would have sufficed. So anyway, look at the cheat sheet, right? I put that there as a guide because, when I do this professionally, right? This is my living. This is how I make money. When I have to solve an equation, and I occasionally do, it's an occupational hazard, I get my own cheat sheet, the internet. I start Googling things. In fact, there's textbooks that are like, okay, here's all the equations that someone in the physical sciences would ever need. And so anyway, it's a famous book. I'll go look in that book. Actually, I go look in that book online because there's a copy online. So the cheat sheet is basically the internet just condensed with the right equations. And for those of you who were looking on the internet, well, you're not taking this class anymore, are you? Okay, part F. Again, not a question I really like too much. It's kind of obligatory that I have to ask something like this because at this point, for one, I've emphasized this over and over and over again, that when you have all these operators, what did I do? D theta. Well, yeah, it's right up there. I have to write it so I can interact with it. To decide ahead of time what this is, how it can be manipulated, think about that extra Friday last week. I guess that was before spring break. Think about how you can transform operators from one representation to another. You always have to apply the wave function. So now a lot of you actually said, well, you have to evaluate it with separability. I actually counted that. That's not what I was thinking, but I don't always know the answers or all the answers to my own questions because this stuff is complex. Okay, so again, if you just apply the wave function or try to do separability, in which case you're still putting this part on the right, that's why that still counts, you would realize that this thing just actually hops over here. And if it's 0 or not depends on the wave functions, right? Not necessarily on the inners of the operator. Okay, so actually I think a fair number of you got that one right. Okay, so part G. Now there was actually a typo on the exam. Not that that caught up most of you. One person had a little problem with the typo, and I fixed it up here. Now what am I doing? I fixed it on the answer key, but I'm showing you what was on your test here, so not to confuse you. So this is the 3D rigid rotor, and let's see, is this a 3D rigid? Yeah, 3D rigid rotor, and this is the theta, the primary mini Schrodinger equation for the 3D rigid rotor. I had to have something on there for the 3D rigid rotor because we just covered it. That was the lecture on Monday before the exam. I have to put something on there. On exam 1, there was a lot of questions on the lecture before. This one, not so much. And the reason is that the 3D rigid rotor is pretty complicated. But I still had to have something on there, and look for that on test 3 as well, and the final. On the final, we have 2 lectures between test 3 and then the final. 2 lectures. There are questions on the final from those 2 lectures. Otherwise, why even have them, right? So there's your lesson there. Okay, now again, we actually did pretty good with this, and what I made a mistake is, of course, I should have had r squared. Instead, I just had r, so that was a bit of a mistake. Sorry about that. I noticed that a lot of you didn't get caught up with that. One of you did. You said, hey, it should be an r squared, and I counted that correct. Okay, so this is what it's equal. And a lot of you correctly pointed out that that is actually a constant. Right now, it's a constant for the problem. So if I am describing a rigid rotor something, then I have to tell you what R is. Now, I could make R 1 nanometer, I could make it 2 nanometers. Well, once I've decided what it is what it is. It's not an operator. Like the hydrogen atom, R is an operator. All the derivatives stick around, and I end up with a wave function with the R, a wave function with theta, and a wave function with phi for the hydrogen atom. On the 2D rigid rotor, or 3D rigid rotor both, there is no wave function with R in it. So this is just a parameter. It's like 1 nanometer or 2 nanometers. So that was the answer there. Okay. So, let's go on. We're out of the what's wrong problems. Again, all of the exams will be the same. Okay, part 2 here. So, again, I would strongly emphasize, look at the cheat sheet. Look at the cheat sheet. Look at the cheat sheet. I bet you didn't think you needed it. For those of you who got this wrong, you weren't looking at the cheat sheet. Now, you have this relationship on the cheat sheet. Sorry, I said y, x and p. Right? So remember that we ended test 1 and began test 2 in the middle of the uncertainty principle, and I told you that it would still be on there. I forgot what it is, h bar over 4 or 2, anyway, it's something like that. Maybe I have it, I have it on my answer. I'm looking at the answer key, it's right in front of me. There we go. Okay, now what I've done here, now let me tell you how this question's engineered. I've taken an equation and graphed it. And I didn't graph it in class, I just wanted to see whether you can hack this, right? Because, come on, that's kind of a high school thing. Can you look at an equation and graph it? Come on, it's senior high school, not senior college. Now, where, of course, it's amped up a bit, is that you also have to know to look for this to begin with. So you have to understand what sigma is. I mean, I even defined it in the question, but you still have to know that I'm talking about the uncertainty principle. And with that, you can look at the cheat sheet and see this. Okay, some of you kind of blew it here regardless because you looked at this and said, oh, well, these two multiplied are a constant, so therefore it's a straight line. No. Do this. Y times x is equal to a constant. Therefore, y is a constant over x. This is not a 1 over x thing. Plug in numbers. Make a constant 1, make x 1. What's 1 over 1? It's 1. Okay, what if x is 2? Then it's a half. And then make an x 5, then it's 1/5. So when you graph this thing, sorry, I'm doing a terrible job here. When you graph this thing, it looks like this. And you can see that that's graph C. So again, if I ask a question like this again, you can hopefully, I mean, if you can't get here, you're dead. I'm assuming you recognize what the question is asking. But if you get a little stuck, just start making up numbers and just graph it off to a little scrap paper. If you have a graphing calculator, that's fine, just as long as you're not using the internet. And also, here's another bit of advice. I noticed that this is not the kind of question that is Googleable. I do have to do that. So, but that maybe allows you to anticipate a little bit what I may ask. Okay, question 3. Most people got this. Again, on average, most people got questions right. The average was around 70, I believe, on this test. And this is one of those do you remember questions. Notice it's early into the test, and so therefore it's early into our middle block of the class. Did you notice that I asked questions in order that we covered them? I do that because you should be most comfortable thinking that way. I think it makes sense to me. Tell me if it doesn't make sense to you, but I thought that this would help you. So this is still an uncertainty principle question. Early in this block, early in the test. Okay, now either you remember it or you don't. It's just that simple, which is that well, you can see it, that the localized one, curve A, has less energy than the localized curve B because the curve B, having lots of knowledge of position, has no knowledge of momentum, and that practically means it has to be going fast. Now, some of you mentioned potential energy differences with it. There is no potential energy, right? The wave functions, it's in a box, and if the wave function is to the left or right of that box, then it has potential energy, but it isn't. You see, the wave functions go to 0 to the left and right of the potential box. In the box, there's no potential energy. Left and right there is, but the wave functions don't go there. So those of you who said there's potential energy differences, that's absolutely incorrect. It's 0. So just heads up on that. Now, 1 or 2 of you said they're equal energy because they're equally high. And that's real bad because that has nothing to do with anything, right? The energy of a wave function is not the highest point. The energy of a wave function is this. When you do an operator on the wave function, and out comes the eigenvalue. It is a look at the hydrogen atom Hamiltonian that we're covering right now. It's hideously complicated. It doesn't come down to what's the highest point on the graph. That doesn't make any sense at all. So for those of you who answered that way, you really need to be reviewing everything because that's off the mark. That is really kind of concerning. Okay, question 4 is very related to question 3. And this was, again, this is kind of a weird question. But I made those videos, and I just thought you would have liked watching them because they're a little bit more fun than not having them, right? So, and because of that, I thought of this question about it and hoped that you were paying more attention. I also gave the answer during the review session, and again, I did that an impossibly large amount of times. And you should know that at this point. The answer is, of course, is that to the right, these things are composed of multiple waves, traveling waves, again from that early lecture in this part of the class. And some of them are moving fast and some of them are moving slow, and that's why the leading edge of the wider graph are from waves that are moving fast, and the tailing edge are from those moving kind of slow. So again, I straight up told you that in the review session. So do you remember the review session? Okay, question 5. Here's how I did this. This is another kind of weird one. What I did was, I know enough mathematics that I can, on a computer, just kind of I can create whatever. You know, I can draw any potential surface, I can kind of type into the computer, and then I've got programs that then solve the wave function, that can solve the wave function for that potential surface that I just I just created. However I come up with that, which can get kind of fanciful. And so what you're seeing is potential surfaces that I created this way, the computer's output as to the wave function. And what I simply did was on D, what I did on this one was I simply got the output and then I mirror imaged it. So you can see, yeah, you can see that up there. You can see how I mirror imaged it. And then the answer to that, again, a lot of you got this right. The answer is that when, of course, the wave function, when the potential energy surface dips, then there should be an increase in amplitude. And you see that, I mean, this is the right answer. So the lowest dip should have the highest amplitude. So when I flipped it over, that was wrong. So hopefully you saw that. Okay, now some of you, when people missed it, they missed it by answering F for some reason. I can't understand that one. That one didn't make any sense to me at all why you would pick F. But B, a lot of you who missed it either picked F or B. Now B makes sense to me. I understand why you would miss this one, and I'm going to exaggerate it a bit from what you see up there to prove my point. So I'm exaggerating this compared to what you see up there. A lot of you said, I didn't draw right. I didn't draw right. 1, 2. Okay, here we go. Okay. Now the wave function, and again, it was drawn on a computer, so it is correct, has a large amount of amplitude in the middle. Well, you can see it up there, right? Anyway, I have to draw it for my own benefit. A lot of you said that the amplitude in the middle shouldn't be so high compared to the sides, and that I gave you partial credit for that because that's actually really sensible. But let me point out why this is actually correct. The reason that the amplitude isn't, so you were thinking that it should look like this. And again, I got it and you got lots of credit, lots of partial credit for that. It's not ultimately correct. The reason that it's not like this, like in dotted line, is because this bump doesn't really have a high wall left or right of it. But this one, it has a little barrier to the right, but it has a hard barrier to the left. This one, again, not a soft barrier to the left, but a hard barrier to the right. The particle doesn't like that, so it doesn't like slamming into this wall, so it avoids it. So indeed, the wave function was correct as drawn this way. But again, I got why you did that, and I gave you lots of partial credit. Okay, 6. This was a horrible one. Some of you got lucky if you didn't get this one on your version. You know, I try to make these all equally hard best I can. Okay, so this is one of the times I know that this gave lots of partial credit on it. To my credit, I gave partial credit. Okay, the thing that is unsatisfying, the thing I don't like about quantum, is how you have to insert your opinion into the mathematics, which is weird. I mean, you're taught specifically to never think that way until all of a sudden you do. So that's great, and I don't like that either. What you have to do with quantum is, and actually I said this on like the second or third lecture on wave functions, is that there can be multiple solutions, eigenfunction solutions to the Hamiltonian or whatever operator, but sometimes you just reject them for some reason. Okay, now, the way that this one works is this is the infinite step potential, if the wave approaches with the same energy as the step, then we know that the Hamiltonian, and you had to do this on the homework, the double derivative of the wave function is equal to the energy minus the potential times the wave function, and what happens is this is 0. So it turns out that a wave function having to go through a double derivative, that actually works, right? And again, you had this on the homework. Now it worked for the finite barrier, but for the infinite step potential, you have to think about it and say, well, is this one of those times that the answer doesn't make sense? And it is. Dx cannot be there. It's just a constant. Now, here's why. Now, again, mathematically, it's a solution, but in terms of practicality, it's not. And you have to insert that knowledge into this stuff. Again, that sucks. But now let me explain why. Let's say that the wave function had a negative slope. Okay. And see, the thing is, it goes on forever. Now, what that would mean is that there's higher probability for the particle to be on the left half of infinity than the right half of infinity through this infinite potential part. Why would that be the case, right? If the wave can get through and skittle along, it can skittle along forever. So there's no reason for it to have a preference to be kind of like to the left, or let's say that a d was positive, then again the wave function amplitude increases to the right. So that says that there's more probability for the particle to be found to the right half of infinity, which again, there's no reason for that. In fact, the mere statement that it's more likely to be found on the right half of infinity is itself not sensible. What is the right half of infinity? See, that by itself doesn't make sense. So now I knew that this was kind of a hard one, and what you're seeing here is me kind of struggling to write questions at times, and so that's where this one comes about. Anyway, so that's the answer. Not too many of you got that one, but I admit I knew it. I knew it was a funky question, but it's just the best I could do, and that's why no one of these questions is worth a ton of points, right? Because I know that sometimes you're going to run into a weird one that you don't know, or I write a bad one, like that one. That's not a great question, but there's a couple of not great questions, but it's the best I could do. And that's why I have a bunch of short questions, so that any one question just doesn't wipe you out. Okay, all right, question 7. That one should have been real easy. Okay, it's a little bit of a do you remember question, but of course the answer is the integral from the turning point. Notice that there was a big hint because I labeled it in the graph of the wave function squared, and that's equal to 8%. Now, some of you said, well, you do that by making the energies equal, which you really meant the wave functions equal, right? You were trying to set up, you were trying to solve this like it was a step potential, saying that there's a barrier and the wave functions are equal. Now, I'm guessing that you were just desperate to write something, which I get that, and there's no telling what you're going to write. One way you could have known that that's no way is that the right answer for this one is that there's no like step, right? So when we did the harmonic oscillator, we never had to use a boundary condition. So you're invoking one. You're saying, oh, well, there's a point where we have to set the wave functions equal, and that 8% comes out of that. We never did anything like that. So that's how you could have known not to have done that. Okay, number 8. Again, a little bit of a bad question, so I tried to make sure that if you had number 6, that you didn't have number 8, or if you had number 8, you didn't have number 6. I do make those judgments when I'm designing the different versions, so that one, there's usually a couple of groups of you know, there's groupings of tests, and I randomly assign you to a group. To make sure that one group doesn't randomly get a hard test, I really double check the versions and make sure that I balance any questions that I know are a little funky, such that one version doesn't have a bunch of those. So I'm actually really careful with that. Okay, number 8 is, again, you haven't seen a question like this. I do throw some of those at you because if I'm just repeating homeworks with like different numbers, then this really gets kind of trivial, right? I mean, you're college seniors. You should be able to hack some questions that you haven't seen before. In this case, what I was looking for was, now some of you, and I gave you partial credit for this, you knew that there would be a quantum number x and a quantum number y, and you were saying that You could have 0, 1 versus 1, 0, and that would be a degeneracy. Okay, that's the definition. So if these had equal energy, you mentioned that this would have equal energy, and therefore you have a degeneracy. Okay, lots of partial credit. You defined degeneracy. Okay, how could you have known you weren't going to get full credit? That's not the question. The question is not defining a degeneracy under what conditions. This is not a condition. It's an example. It's not a condition, right? I know that's subtle, but it's a difference between getting full credit and not, okay? So you want to make sure you get this down. This is the definition of degeneracy, but that was not the question. Of course, the real answer is that the energy, of course, is it actually is going to be this, right? So you had done a couple of these to know on the homework exam before this, and so this is what made me think of this, is that you had done some homework examples where we had two wave functions multiplied that the energies just end up adding, dimension x, dimension y. The wave functions multiply, the energies add. So for this to be true, you had to have the same, these numbers had to be the same, the angular frequencies. And of course they, in turn, now if you said, some of you said, you said W, X, Y must be equal, full credit. Now you could have also noticed that this, I think, hopefully I'm writing it right, spring constant over the mass. You could have also, the real answer is the spring constants need to be equal, and again, that would be full credit. So there you go on that one. Again, just a hint here on being careful about not answering the question asked. Defining it, restating the question is not going to give you full credit. So look very careful. I actually really look at these, when I write these exams, I look at it over and over again to make sure that the question is actually very explicit. Okay, next one. Okay, the only thing I can tell you that almost everyone got this one, if you got assigned this question. Some of you wrote, it's like a whole page, and you could have said one word, separability. Now, I did comment on most of your exams, and a lot of you got the same comment from me. Just say separability, right? Separability. I want to see if this is separable. Okay, so I told you, and the reason I thought of this, by the way, again, this is what I want to get across to you. It's like, what am I thinking when I do these? Is that whenever we have a Hamiltonian, we have to solve it. What does it even mean to solve, right? I've been talking about this since Planck distribution. What does it even mean to solve? It means to find the wave functions. Now, with the wave functions, then you can solve the energy. So that's why I'm bringing this up, because it's kind of ambiguous. In an eigenvalue equation, what are you solving for, right? Because there's two unknowns, right? There's the eigenvalue and the eigenfunction. Which one are you solving for? You're really solving for the eigenfunction, and once you have that, then you can get the eigenvalue. There's a natural order to this. So when it came to this thing, obviously I just made up some stuff. And that should be a hint that the answer is kind of simple. When I'm doing stuff like that, the answer is usually simple. Because, I'm not going to ask you to solve any Horst wave functions, right? So that means the answer can't be anything complicated. And the answer, of course, was separability. Okay, number 10. I'll probably do questions like this. Actually, on the next test, it doesn't lend itself to math puzzles. But on the final, look for that. I've thrown a lot of mathematics at you, trying to, there's always a chance some folks come in to be blunt, and to be blunt, some of you still don't know any calculus. I don't mean to be rude, but some of you still can't take a derivative, and you're probably going to get a D, and that's why. And you're not willing to do anything about it. You're okay with a D. So here we are. So you're going to get a D. But to try to get those of you who don't want Ds, but you are deficient in your math, that's why I've been having these math questions on all of your homeworks. Now, I'm not going to do that anymore because I'm kind of out of questions. What I'm now going to be doing from now on is asking review questions from the beginning of class because your final is comprehensive. So no more math questions. But in this case it was because I keep throwing math questions at you. I just want to reward that effort, and I will do that on the final. So a lot of you got most credit if you did this. Unfortunately, a lot of you stopped here. You stopped here, and I don't know why. I mean, keep going. Right? Here's the hint. Here's the hint how to know not to stop here. This got you a little over. That got you 4 points. You notice that I always make the questions odd number. It forces me to give you more than half when you've got half the answer. It's to your benefit. All right. So what about this? If you wrote this as half credit, but what I really wanted to see you do is this. Again, I defined it, right? If I never defined how u was related to x, this would have been your stopping point because you couldn't have done anything. Well, why did I tell you that u was x squared? Why did I do that? Because I meant you to go further. That should have been obvious. Now, some of you then put this, and you got most credit, maybe you 5 points, but what you really needed to do was, of course, remember when I was talking about converting Cartesian to cylindrical coordinates, this is what I just did. I mentioned that you need to not retain any of the Cartesian coordinates. So here, if you're converting x to u, your final answer can't have an x in it. So you have to do that last step for full credit. So anyway, math puzzles this, math puzzles that. Okay, 11 was a review question. Do you remember? Again, stated multiple times in the review session that the 2D rigid rotor is really kind of interesting because it's our first step into multi-dimensional this and that. And as you saw with hydrogen, that gets real complicated really freaking quick. But the 2D rigid rotor is multi-dimensional but not mind-blowing. So that's why I spent a long time on it. It's the oasis before the storm, right? The calm before the storm, the oasis in the desert. Because it's still basically a free wave. And by now, you're probably thinking, oh God, that was really easy. Remember I told you that? I said, there's going to come a time in this class when you're going to look back at the free wave and say, oh my God, that was so easy. Yeah, it's now. So anyway, that's why I harped on that. And the answer, of course, was, for that question, it's a free wave because it's basically e to the I kx, except it's e to the I m phi. And it's like a particle in the box because it has a boundary condition. So I was looking for a boundary condition. Okay, and then number 12. Okay, this was a bit of a screw up on my part. 11 and 12 are kind of the same question. That was a bit of a screw up on my part. 12 is a boundary condition. So I gave lots of partial credit, depending on what you came up with. But again, that's the do you remember. It's a boundary condition. Okay, 13. Lots of partial credit on that. Most of you got full to partial credit. But I was doing this because this was the last thing in class on Monday's lecture before the exam. And as I had strenuously told you, that will be on the exam. I always have stuff from the last lecture. Now, in terms of let me tell you a little bit, so I have to write this down again to interact with it. I know you can see it above my head. Now, I know this was confusing, and I know I can honestly look at myself in the mirror and say I've done my best, but I know that it's still confusing about how to understand separability, because I've said over and over again how these are miniature Schrodinger equations that are solved on their own, yet there is some funkiness to them about how they add up together to a constant. So, it's like yes and no. Okay, now when it came to 2D particle in a box, what happened was, when you separated the X and Y particle in a box, each was equal, you had a mini.
I'm so sorry.
Visitors. You had a mini Schrodinger equation for X, and you had a mini Schrodinger equation for Y. And I remember this is when we started multidimensional, and it was equal to the total energy. And so I mentioned to you that each one was equal to a component, EX, EY, where each is probably half the total. Okay. That's how that problem works. Remember, the unsatisfying thing about quantum mechanics is you kind of have to just figure things out. And in this case, for the 2D particle in the box, you have to just divvy up the energy into two pieces. You have to just know that that makes sense. And I know that sucks, but this is why we have class, to get that across, because I don't know what else to do. Well, that makes sense, doesn't it? Okay, now, some of you tried to invoke that on this, and I gave full or partial credit, but it doesn't actually work for the 2D rigid rotor. Now, the reason that is because the energy is fully sucked into the theta one. Now, then some of you said, well, then it has nothing to do with it. Not quite, because this, now remember, this was like the parting thing I said on Monday's lecture before the exam, is that that's equal to m squared, minus m squared, right? And so therefore, and m is a constant, so therefore, all of the theta deal is equal to m squared, so that minus m squared plus m squared is equal to 0. So it does affect it, right? So that's the answer. Not too many people fully got that. A lot of you, so be careful. Like here's what got some of you got some points off. You said things like, it does, it doesn't affect it. Okay, I can't give full credit to that, because that allows you to say anything and win, right? That doesn't mean you know anything. I don't know what you know. It makes it impossible for me to evaluate. So you put me in a very bad position when you answer questions like that. So anyway, you see the full answer. And again, look out for things like that. One other bit of advice, look out for answering. I've had one or two cases where people literally say everything they can think of. And here's the problem. Inside of just writing whatever down is the answer, mixed in with a lot of things that are not applicable or wrong, you're not going to get full credit. So I won't give you 0, but you're not going to get full credit. Okay, last bit. What I was looking at, okay, on number 14 here, was a handful of you actually determined what the change in energy is. The reason I thought of this question is because I was kind of annoyed when I was talking about spectroscopy, that is the energy of an excited state minus the energy of the ground state. And a lot of you were approaching that question, remember that question about Lindsay, or the FTIR question with D2 or H2? A lot of you were just looking at the energy of the ground state. Well, if that doesn't make sense. I mean, if the photon's absorbed, you're not going to be in the ground state. You're going to go probably to your first excited state, and that energy difference has to be accounted for by the energy of the photon. I mean, again, you've had this since high school, but all of a sudden you're working with delta E and you're setting it equal to the ground state energy, and there's no way that's going to be right. So this is what made me think of that question. Now, a lot of you basically answered exactly that way. You said, well, the ground state energy is going to drop, so therefore that's the answer. The energy drops. You're not going to get full credit because you're not putting this in context of an energy difference. And maybe that relationship is no longer true. Just because the ground state energy drops doesn't mean that the excited minus ground state energy, the energy difference, it doesn't mean that that drops. It actually does, that's happenstance. It is because this ends up being let's call the excited state M2, let's call the first excited state M1 just for the hell of it, and then there we go. Now I is mass r squared, so if r goes up, then the change in energy goes down. So that's how you work your way through that. Okay, 15, I was surprised how many of you struggled with this. You know, with COVID, this and that, I'm okay if you just write the answer down. And I would hope that you would just, having worked some similar problems on the homework, that you would just write down the energy of one plus the other. That would have totally done it. And some of you, I think, did that. A handful of you did that. So look, I mean, I know that this is kind of a bear to work through. I won't even do it. But it's just, geez, I just thought this was unbelievably obvious. The energy, well, here. All right, double derivative. At this point, a free wave should be, I would have thought that would have been unbelievably simple. Minus h bar squared I squared k squared over 2 times the mass is just h bar squared k squared over 2m. And again, I have to write out mass. Now the y was the sine function. You still have the same constants. You're just doing the double derivative with respect to y. I know I forgot that little 2 there. That messed up one of you, but for the most part, I think a lot of you realized I had just been stupid and figured it out. Okay, and of course this is going to be minus goes away from the double derivative. H bar squared pi squared over L squared. Okay, and then these two added together are the answer. Last bit, what some of you did, which just kind of shocked me, was you just left out the constants. You got a lot of, you did the mathematics right, but you just left out the constants. Why'd you do that? I mean, yeah, at this point, I would think you'd be sick of seeing this one, energy of a free wave. You've been seeing this for six weeks, almost every day. I mean, that's why I thought, I would have been fine if you just wrote the answer down, because at least this one, you've seen it so many freaking times. How could you not know it off the top of your head? So, anyway. Okay, 16. We're almost done. 16, if you looked at your exam, of course, I have it set so that you can see my answer at the bottom. It may be, I might have had typos, right? Sometimes I catch a typo and I fix it later. I can't actually go back and edit these later. It's impossible. Okay, where a lot of you got this wrong, and I understand why you did it, you tried to solve it this way. I'm sorry, this single derivative. Look at me, I messed that up. You tried to do it this way. That doesn't work. This is how you solve the energy. Now, because I knew a lot of you would go down this route, and it's not, sorry, that doesn't look good, and that isn't going to get you what you need, I wrote in the question, it's right up there, and the wave functions had to be continuous. So that's all you need to do. It says it. When I have a hint, don't ignore it. I never put a hint unless it's basically the answer or will get you immediately to the answer. Okay, so this is non-productive. Now, one of the things you could have done is, even if you're going down this route, this is what a lot of you do. A lot of you evaluated each, so if you did this, you're not good, right? But now let's look at the individual parts. Let's say that you did this part, because this gives you the answer. You got a e to the 0 equal to b L squared minus 0. Now, a lot of you were writing this down, and then you kept barreling down the wrong direction. But look at what you got. And what you're looking for is b squared over a squared. Come on, how can you not just do some rearrangement like that? Oh, look at that. You got b squared over a squared, and then square them, and that's the answer, right? So the lesson here is look for the hints. Now again, I understand why you did that, but I didn't want to make the question too complicated. So to prevent you from doing this, I had this hint. Don't ignore the hints. Derivation questions usually aren't mind-numbingly complicated, because I know that this is stressful and you don't have a lot of time, so I make these easier than you think. And just notice that, as you saw me walk through it, notice that when you had an equation with A and B in it, and that's basically all I asked you to do, that you were right there at the answer. You should have stopped when you did this. A lot of you did this, but you kept going and going and going in circles. And you should have recognized at this point you were basically at the answer. Let's see, okay, last one. I thought this one would be a giveaway, but now this is something that really got ugly. Very few people got this one fully correct, because I was pretty shocked how few of you know what an eigenvalue is. Almost no one in the class knows what an eigenvalue is, and I could not believe that. I mean, we have gone over this so many times. An eigenvalue on a wave function. Okay, so I'm not going to bother to do it. This is the value. This is the function. Most of you kept them together. This is not the eigenvalue. This is the eigenvalue. If you keep the function with the value and say that the whole thing is the value, you cannot do anything right. Nothing is going to work out. So part A was, what is the square of this, of the sorry, it says what's the square of the eigenvalue? I should have said that. And so, that's the square of the eigenvalue. Because that's the eigenvalue. That's the eigenvalue. Okay, now for some reason, some of you decided to try to do this. And okay, that's nuts. And then when it came to part B, you did it with the operator way. Okay, that's weird. Right? So when it came to this one, all of a sudden you did this. Then you just used the operator, which of course just brings down minus m squared. Okay, so look for that. I didn't say do this, I said do this. Notice how similar they were, but some of you used a completely different approach to solve the two clearly related problems. You can get the right answer this way. It's still h bar f. It's still the right thing, and you can still square it. But you wasted a lot of time, and that was not sensible. Okay, C, I counted C depending on what you did for part A and part B, but clearly it's 0. Notice that you could have figured it out because part D told you part C was 0. It's right there. I told you if sigma jz is 0. Clue, that's because part C is 0. Why would I say that on part D if it's not the answer to part C? Have you been taking my class? Had you not seen me do this, I don't know, every time? God, I mean, I would have given you full credit if you just put 0 there. Now, normally I wouldn't do this. Normally I need to see the work to get full credit, but COVID, this and that, you could have gotten, well, it's only 2 points, it's not a big deal, but, anyway. Okay, last bit. Okay, so JZ, the sigma JZ is 0, and so if sigma JZ is 0, then you should have realized that, of course, the only way that makes sense is if the knowledge of the angle is infinity. Now, the way that you should have known that is because, remember, the 2D rigid rotor is the same thing as the free wave. The free wave momentum, the standard deviation, the variance of the free wave momentum is 0. The standard deviation of the free wave position x is infinity. Remember, that's why I kept alluding to that. This is the same thing. So the lack of knowledge of angle is infinite. That means you don't know what the angle is. Anyway, Okay, so I've gone over quite a bit, so hour, 5 minutes as opposed to 50 minutes. Sorry about that, but again, I'm doing this to help you on your final. Your final is worth all your other tests. Even if you got a D, you can ace the final. I've seen people do it. I have seen people go up not 1 grade but 2, and that's rare, but I have seen plenty of people come into the final with a letter grade and come out with a higher letter grade. I have occasionally seen people do that 2 letter grades, occasionally. Now, I'm not telling you that that's feasible, that that's likely. It is possible, right? And that's because that's why I create the scoring system that I have. For the most part, you're consistent. You're not going to screw yourself over. But if you really have that fire to do better, you could go up 2 extra letter grades. That is possible. And that's why I spent a little extra time on this, to help you do that. Okay, but I have gone over. Enjoy your weekend. I know you're watching this before the final, but again, hopefully it'll help. Okay, I'll see you all on Monday.